Okay, so at some point in the semester, early in the semester, I'm gonna let you guys sign the NDA with TSMC. So there will be a NDA with two companies, TSMC and WDC. So WDC provides the IP core, the CPU core, and TSMC provides the library. It's really interesting to tell, since most of you guys are taking both classes in the same semester. So all of you must sign NDAs with both companies. So how that works, it's a little bit complicated to explain how that works, but let's try to do it for now and see if you can understand what's going on. So WDC is a company designed the 6502 microcontroller many years ago, and so back in the 1980s, they just have to hand draw the entire integrated circuits on the poster. It's a huge paper. If you have ever met with Mr. Bill Mensch, and when he designed his CPU, it was drawn on the poster. Every single transistor just hand drawn on the poster, and eventually there was some technology I've never seen before, and printed on the silicon wafer and fabricated the CPU. So by that time, we didn't have cadence. We didn't have electric VLSI. So there's no way to automate your design with the computers. So the problem is we didn't have schematics. We didn't have RTLs, which is Verilog code for the CPU. So everything was designed by hand. I think in early 2000, he started a new company called WDC Western Design, Western Digital Center. It's not Western Digital, okay, which is a way bigger company. It's just the Western Digital Center. It's a company still selling all these 6502 microcontrollers for a lot of industries that are still using that microchip, even though it's really old, but it's still functioning. They hired a digital design engineer whose name is David Gray, who worked with Ian Van Horn for almost one semester closely, meeting probably like 2 hours a day, trying to figure things out. So David Gray is still working with WDC, and who is a front-end engineer. What does that mean, front-end? So he only works on anything about Verilog, so digital design, Verilog, or verification, or simulation, but didn't touch anything on the back end. So back end, which requires another team, okay, to do all the layout and timing optimization in Cadence or all these digital design tools. Okay, this is what Ian did in the past semester in the fall, for the whole semester from the senior sem, so on Cadence. Okay, so this backend design will be something we are going to do for the second half of the semester in CE433. Okay, so that's why you need to sign the NDA and the contract with TSMC, because TSMC is providing the libraries, all these IP cores, for example, flip-flops, MUX, and all these smaller cells were already designed in standard blocks from TSMC, because TSMC is a foundry, it's a pure play foundry, who doesn't do any digital design, but just the fabrication, which is the best fabrication or integrated circuit design foundry on this planet by far. It's taking probably more than 85% share of all these advanced chip design, including all the Samsung and the Snapdragon and all these Apple chips. Okay, so we are working with TSMC. The goal is to have you guys be ready on the first day when you are getting a job in the IC industry. So we are using TSMC's IP, standard cell library, for the backend design in this class. However, we are also trying to have the RTL, which is a Verilog core from David, that we can implement it on the IPGA. So which is the Ultra IPGA? I think I showed you really quick. to this FPGA board. So if you implement all the RTL into this FPGA board, you can also get a microcontroller, but it's a soft core with the memories and pins. It's a soft core in the FPGA, and you can use the FPGA the exact same way as the ASIC. If you get ASIC from TSMC, it has the same number of pins, the same functionality, the same clock speed, and you can write the same code into that ASIC as whatever you can write into the FPGA soft core. Same stuff. Okay, so this embedded system class is going to do the FPGA type of ASIC. Sometimes it's getting confusing when we are talking about ASIC. We're trying to just refer to that specific IC design from the foundry directly, but not the FPGA. But however, in the industry, some people also call that FPGA as ASIC as well. So in general, if we want to differentiate the FPGA type of ASIC from the ASIC or from the foundry, we'll just call the foundry version ASIC, but the FPGA version just FPGA. But if there's no the foundry version of the ASIC available, then we just call both ASIC. You know, it's a little bit confusing, but just let you guys know what's really happening here. So we need to sign the NDA for both companies. Hopefully that's going to happen next week. And make sure that you are not disclosing any of the documentation from the two companies. Just keep it within this class, right? Okay, so let's come back to this tutorial and see the tasks for today. All right, let me return these ones to you guys first. Any questions or quiz? Alright, so I have a second quiz today later for modeling methods, all the three modeling methods, and the hierarchical model methods as well. Okay, I'm gonna code it in front of you, just let you know how to start from scratch, right? And for students also in the VLSI class, for the second half of the semester, will be probably totally on the Linux server, and you'll probably use VI daily. And for people who are just in the embedded system class, when you are working in the company, the tools like Synopsys, which we didn't purchase, but all the design tools are based Linux based, so eventually it has to be VI. That's why you're asking me why do we have to use VI as an editor. It's just a way to practice. Okay, eventually it's going to be all the tools will be hosted by Linux servers and will be Vim. All right. So first we want to talk about is blocking and non-blocking assignment. Like this. There are two different assignments, which is a little bit different from the C language. So blocking and non-blocking, which one is blocking, which is non-blocking? So this is blocking. Okay, equal sign is blocking, and this with the arrow here, less than operator, is a non-blocking. Okay, so it's the assignment operator. It's not a comparing these two values. Just keep that in mind. What's the difference? So whenever this guy is assigning, it's it assign x to y0, and then y0 got updated, then y0 assigned to y1. So it's always updating. So whenever the first one is being operated, the second one is blocked. So that's why it's called blocking assignment. Sorry, it's tiny. I just zoomed in. Okay? So for example, if you just look at the first three lines, after the assignment, what the values will be stored in y2. X will be stored in y2 because it's blocking the operation of the second line when the first one is operating. So the first one will assign x to y0, okay, and the second one is waiting for that when that is done, and then y0 will be assigned to y1, so on and so forth. So eventually, y2 will be updated by the whole lines above it. So eventually, x will be stored in y2. But for this one, it's non-blocking. You can imagine these are just the three signal lines, and you got a one single clock controlling the assignment. So eventually, one clock arrives, all the three values will be assigned to these variables. So you're expecting x to be given to y5, it won't happen because x will be given to y3. So if you want to give x to y5, what you have to do though for non-blocking? Just clock it by 3 times or twice, right? Yeah. So the first time the clock arrives, boom, all the values assigned to the left. So we got y3 storing x. Okay, so y3 will be updated. So got a clock arrives the second time, right? It's gonna update y4 with whatever stored in y3, which was x. It just needs multiple clock cycles. Make sense?
Yeah.
And the clock is fast, pretty fast in digital systems, which is totally fine, you know. Eventually x will be assigned to y5 after a few cycles. It's just that how it works. So for in your experiments or all these examples, depending on what you really need, so you can make a decision which one to use for the design. So it's the assignment, blocking and non-blocking assignment, and time delay. Let's directly jump to here. This example. Sorry. This example here. I tried different configurations of the projector just after the lecture from last time. It didn't work well. So this is probably the best version we can give to you guys. It's just so interesting. I think the one way I can do it is I can extend my display over here. Will be slightly better. Let's take a look. If I extend it. All right, but the thing is I have to drag this one here. So I have to keep looking at that wall when I'm talking. I think that's probably fine. No, it doesn't work for me. My neck pains. Take it back. I'll just zoom in, all right? Just zoom in. Let's go to this example here. All right, the design. 2 design files. You can just scroll down to this example on your desktop. Just take a look at this one. This is one of the examples, one of the homework assignments as well. I think I asked you to change one of the time delay to the different line, but it's the same concept. Let's take a look at it. Let's take a look at this. So the design, digital design file is over here. It is a module, right? It's a module with the digital design. Here's the logic. Here's the logic. So according to the operator precedence, which one will be executed first? You got 1, 2, 3. What's the order of execution for all these operators? And, right? And, or, and then XOR. Okay, if you look at the circuit, here, it's not this circuit? Probably not this one.
That looks right.
or and XOR. Okay, this is for out 1. Yeah, that's right. Yeah, so for output 1, it is or and XOR, right? Yeah. For out 2, it's just basically an inverse of in 2. Okay? Yeah. That's what out 1, out 2 are. Now let's take a look at the code. Okay, what's happening here? All right, this one. So it has a time delay for 20 nanoseconds for out 2. So when you are hand drawing that waveform, you should include that 20 nanosecond time delay in here. And so you can find out out 2 is always the inverse of in 2, however with the 20 nanosecond delay. So what is in 2 and in 1 and in 2? What are these two signals? Depending on your simulation, right? Yeah. The chip is the chip. It doesn't have anything in it. So depending on the user, I want to inject this kind of signal to it, then just use it. So here's a test bench, which has all the signals. It's already zoomed into the maximum. Take a look at it. I'm going to give you a few minutes. Tell me what's going on here.
So it's initializing the input ports as 0.
Mm-hmm. Yes, yeah. Initializing with zeros, and then what?
Then there's like the 100 nanosecond delay.
That's right, yeah. So how many times this will be executed over here? Initial, begin, end, for all of them, right? Initial, begin, end, right? So it's being wrapped in this initial, begin, end statement. So how many times this will be executed? Just once. Yeah. Keep in mind, just once. And anything being put into the initial, begin, and end statement will be only executed for once. So the values will only be assigned to the variables for once. But however, you can repeat it by adding this repeat statement over here, the keyword. So repeat by 4 times. So initially you have in 1, in 2 to be zeros and have a 100 nanosecond time delay, and eventually you repeat this by 4 times. So this is a little bit low resolution, but this is a curly bracket. You can probably see it on your desktop. It's a curly bracket. This is concatenation. You are combining these 2 bits into one binary number. Concatenation means concatenation, okay? If you have A0, B0, these are just binary numbers, okay? But if I do this, B0, comma, A0, curly bracket, this becomes a 2-bit binary number. 2-bit binary number. So this B is not 0 anymore. A 1 here for B0 means what? 2. Okay, that's the difference of concatenation and 2 binary values, 1-bit binary values. Because right now it's a 2-bit binary value, and this guy becomes an MSB, not an LSB anymore. So whenever this is getting toggled, it's actually getting a 2 added to the number. Okay, so it's concatenation. You're combining 2 binary numbers into one 2-bit binary number. Okay, so in that case, if I do this, let me start a new paper. Oh, there's one of the labs using this concatenation for digital outputs. So it's important to know it. A1, comma, A0. This is a 2-bit binary number. Okay, equals A1, comma, A0 plus 1. What does that mean? What is this doing? Repeat it for 4 times.
It's just incrementing by 1.
Incrementing by 1. So this is 2-bit binary number starting with 0, 0 because of the initial begin assignment. It's adding 1, so it's going to be 0, 0, 0, 1, 1, 0, 1, 1. So it's just going through all these combinations, okay? Trying to verify the logic. So in this Does that make sense? Pretty easy, right? Okay. Any questions on this by far?
Actually,
What's that?
how does it deal with overflows? Like, let's say you repeat
Or
5
yeah,
times.
it's gonna because you only have 2 bits, so eventually the overflow will be gone.
Yeah.
You don't have anything to handle it over here, which is fine.
So it just, yeah, okay.
It's gone. Yeah. Yeah. Any other questions? Okay. So this is the difference between, as always, when you you learn C at the very beginning, so always have that C++ concept in your mind, handling overflows, how the computer handles it. So right now, starting from this point, you are a hardware engineer, which means you design everything in the hardware. If you don't have anything to handle that overflow, there will be nothing to handle it. It's crystal clear to you in front of you. There's nothing hidden there. It's just so clear. If you don't design it, you don't have anything handle that bit, there won't be anything to handle it. Keep that in mind. Okay, you are a hardware engineer right now. Okay, now take a look at this. Come back here. So it's adding a 1 to it, so it's incrementing by 1 each time, repeated by 4 times. So it's just adding a 1 to this 2-bit binary number. And that's the top level. It's a test bench. Because here's the core. Here's the core, right? That's the digital logic. And now you have another layer outside of that core to add signal to it, to the ins, and then you are probing the outs, right? So you are probing the outs. You know, the way to probe it is just have an output over here. Eventually you can visualize it in the simulation tool, right? Okay, so you have to include the core as a UUT. Remember last time we put a DUT there. Why is it UUT this time? It's just a name. So last time the device enter test, and this time it's the unit enter test. No difference, right? Just a name. So one quick question. So the name right after the dot is a signal line in the submodule or the signal line in the test bench. We talked about that last time in the lab, but just trying to remind you about that. It could be confusing. Sometimes they're using the same name. So it could be very confusing. But this time it's a different name. I already have the answer for you in this code. So this signal right after the dot is a signal in that UUT or in the test bench. Hey, this is the test bench signal. It's out 1T, so this must be the submodule signal. So keep in mind, the signal line right after the dot is a signal line in that submodule or the UUT. Okay? You just have to memorize it. Okay, that's the syntax. Okay, then you make the connection, right? So dot, this signal line from the submodule, make the connection to the test bench. So eventually, whatever the logic output from the submodule will be delivered to that output. And whenever in your simulation you are looking at this output 1T for the output of the logic. And the same concept for other signals. All right, that's how you can make a connection in your test bench submodules and within the submodules. That's what I'm trying to talk about for this class. So let's look at the next example for the hierarchical design, which will allow you to make connections within submodules and then eventually connect everything to the test bench. Okay, let's do that example after this one. Let's finish this one first. I'm sorry, I forgot. We were where we were here. Right, looking at the diagram. Looking at this one. What is given here? What is given? In1 and in2 are given because they are just incrementing.
Yeah.
And let's see if that's true. So take a look at the 100 nanosecond time delay. Right, every time you add, before you add 1 to it, you have a 100 nanosecond delay because you want to just stretch it in the time domain so you can see the signal, right? Otherwise, it's just a dot oscillating back and forth. So you want to stretch it in the time domain. That's why you give a 100 nanosecond time delay. Okay? Make sense? Yeah. Okay, cool. So let's see. Let's start from beginning. If you got lost, let's start from beginning over here. So 0 and 0 for both inputs, no problem, right? Okay. And now, well, 100 nanosecond delay. No problem. Keep in mind, every time you run that Verilog code, it just update the value to a dot. Then you extend it by the time delay. Keep in mind, okay? So dot zeros, 100 nanosecond time delay. And then another 100 nanosecond delay. Why? Because it's the first 100 nanosecond delay and the second one within that repeat statement. So the first time you got 2, but later on you just got 100 nanosecond time delay, okay? So now, right after that, it executes it, it's adding a 1, so it becomes 0, 1. Becomes 0, 1. And after 100 nanoseconds, it becomes 1, 0. So it's adding a 1 to it. And then update it to these dots, 2 dots, to 1, 1. And then to these 2 dots, to 0, 0. Why? Because it overflows or carries out, okay? So it resets the 2 bits to 0, 0s. So these are given. If you are having a similar problem in the quiz or the homework assignments, you can definitely just handle the signal inputs easily because they're given, okay? For out1, let's look at that later, but for out2 is very simple because according to the test bench, out2 is basically just the inverse of in2, okay, with a 20 nanosecond time delay. So in that case, it just invert in2 but delay it by 20 nanoseconds. Is that easy? Since you already have in2, all right, just look at in2 and draw out2. Invert it and then delay it by 20 nanoseconds. Easy. What about out1? Out1 has some kind of logic over here. So how you have to plug in the numbers of the in1 and in2s and do all these logic operations, eventually find out out1. But there's no delay. There's no delay. So what that means is right after 100 nanoseconds, you update your out1 by using this logic operation. You just update it. Since in1, in2 are given, right? You just plug in in1, in2s in it and update out1. So you can eventually find out out1's logic, okay, by looking at in1, in2's signals during that time frame. So whatever in1, in2s are, right, you just directly draw out1 over there. But make sure that, see, because whenever that logic operation is getting executed, you got the 2 dots updated, right? So the 2 dots, you just plug in this 2 dots value into that logic to find out this dot. That's it, and then extend it by 100 nanoseconds. That's it. Any questions on this? No? Easy? All right. Now let's move to this one, hierarchical design. We have 1 more hour, so let's work on this, okay? I think we have a different problem in the quiz, but I'm gonna probably do this example in front of you and see if you have any questions on this. All right. You know, sometimes the vim commands I can even forgot. There's so many of them, but I remember the major ones. If we do this, is that lecture 2.b? Set GUI font. I know this is annoying, but in Linux it's always like this. Let's make it bigger. 18. Set number. Hopefully it's visible. It's not quite visible. 24.
Oh, is that an asterisk you're using to set the?
What's that?
Oh, it's like GUI font equals asterisk, so you can like set the.
Mm-hmm.
Okay.
Mm-hmm. So for hierarchical modeling methods, how do we do it? I mean, for data flow, structural, behavioral, you already practice with it in the quiz, right?
Yeah.
So it's gonna be on the quiz for today. Just take a look at it. I'm gonna give you probably 10-15 minutes before we do the quiz to look at it. It's closed book, closed notes. Keep in mind. So for this one, hierarchical is very similar. These gates are really simple, but just in case in the future they might be very complicated digital blocks. So in that case, we just have to deal with the ports inside of the logic itself. But the logic will be described in the modules, which we just use gates to represent these complex digital blocks for now, just making things easier. So the way to do that is you create individual modules for all these gates, which sounds ridiculous because these are just a very simple operator, right? But now we just treat them as modules, because in the future there might be very complicated blocks with a lot of logic inside. But now these are just one gate. Yeah, I know it's, let's just do it, okay? So for this one, is that I0, I1, right? And output is or out I. Let's just call it or out. What about that? So don't forget the semicolon, okay? And that's the input I0, I1, right? And output is or out, so no problem here. And then if I just do assign, it doesn't matter what kind of model method you use for individual modules for hierarchical. So hierarchical is just another methods to model a bigger system. So assign or out to I0 or I1, right? Okay, done for the first one. Escape and colon right. Colon right. Okay, the first module done. But in the future, this could be a more complicated logic in the future. But now it's just a one module for this gate. Okay. What about the second one? It's just the AND gate, right? Module. It's still I0, I1, and out. Don't forget this semicolon. Input I0, I1, semicolon. Don't forget that. Output, and out. All right, and then assign and out to I0, and keep in mind it's different from C++. And or not. This is not. Okay, this is not for C++. This is not for Verilog. So and I1. So you're done with the second module. And the third one. Okay, so let's show you something can simplify it. Shift V. Okay, copy. I just copy everything and press Y and press P. Okay, and so is this gonna be a problem? No. Same name for the sum modules. And this will be X or L. Okay, so for example, I had this one over here and I want to replace it. Just directly press R. Okay, press R. You don't have to delete it. Press R and replace it. So that's X or out for the third module. And here I have an extra line, empty line. I've just pressed DD for twice. I can delete it. And then I need an inverter, right? So I'm gonna do P. Okay, so P is gone. I have to copy everything. Y, right? And P. So this one, I only have one input, which is, let's just call I0. Doesn't matter. Some modules doesn't matter. And
did you have to change the module in the third one as well? 10, 11, extra?
yeah. I haven't given a name, right?
also the output's supposed to be PS4, right?
Output what? Output XOR out. Oh, here, right? Okay. So this is AND gate. All right. Save. Anything else here? This is. I know the font looks ugly, but just want to make it bigger. So this one is right, and this is also right. Oh no, this is not yet. So this is a NOT gate. Okay, and input I0. It's okay. It's all right. Not out. Okay, so the modules are done.
I'm confused why for the third one for the assignment, why it's I not and I one and not like.
Which line?
Out.
Which line?
Or for the third one for the XOR gate.
Mm-hmm.
On the assignment, I'm confused why it's I0 and I1 and not and out and or out.
Because these are some modules. That doesn't matter. These are some modules within that module. So we will eventually make a connection in our top module later on.
Okay.
So the sub modules signal lines doesn't matter. They can have the same names.
Okay.
Mm-hmm. That's a good question. That's why we're using hierarchical modeling. What's that?
I don't understand, because isn't it?
It doesn't matter. Well, I'm going to show you. I'm going to show you why. Okay? So imagine that an AND gate, there could be like billions of AND gates in the CPU, right? And billions of OR gates as well. So they are being used repeatedly in your top module. And the top module, when you are going to a higher level, and eventually all these port names within the sub modules are not visible to the higher levels of modules. That's one of the design ideas in ASIC or IPGAs. So we'll see the same sort of concept in VLSI design. So that's why it's really interesting to take the two classes at the same time. So the layout names are using the same concept. When you can name, let's say that. So two AND gates have the same port names, right? But eventually they are being brought into the same top layer, but they have the same names. But you are not necessarily connecting all the inputs to the same line, right? This AND gate can be used for a totally different purpose, but they have the same names. So it doesn't matter.
You can't have two modules of the same name. Like you couldn't have NOT gate and NOT gate. Module, NOT gate, module, NOT gate.
That's right. Yes. That's a gate name, right? It's not a port name. But the port names can be the same. But the module names has to be different because there are different modules. Okay? Great questions. Now let's connect them together. So what's happening is we need so all these things are individual modules, and we want to bring them together onto one breadboard. You can imagine just a breadboard or a chip, whatever. And then you call the whole thing a system or a top module. That's what we are doing here. It's called the hierarchical design modeling method. It's a very important modeling concept over here. So how do we do that? Think about it. So first we have to instantiate all these gates in the top module, right? We have to instantiate it, every single one, so we can bring them into one top module. So lowercase o to start a new line, start typing, right? Do this. So here's the top module. I'll just call it top. So the top has how many ports? Look at this top. Look at this guy. How many ports?
There's 2 input ports and 2 output ports.
Yeah, so 4 ports. Okay. Probably it's better to call it different name. Did I use in? I didn't. Okay, let's just call it in 1, in 2. All right. Okay. I'm gonna skip the wiring thing for now, but let's just instantiate it. So let's say the first one, OR gate. So this name has to be the exact same name as the module. That's how it's able to understand it, which one you want to instantiate, right? So it has to be OR gate. So I'm trying to bring this one to the system first, OR gate. Let's call it OR gate 1. See, even though we only have one OR gate. What's next? Make the connections. The top module is whatever the outer layer box, right? So now we wanna so for the entire system we have in 1, in 2. So if you look at the diagram over here, let's connect I0 to in 1 first. How do we do that? Dot what? In 1 or I0? I0, I just told you guys. So the signal line right after the dot will be the signal of the sub module, not the top. All right? So it has to be I0. Connect to where? In 1. Okay? Sometimes you'll see people organize in a different way. They like to do this, but you know, doesn't matter. You keep it in the same line or the second line, doesn't matter. Let's just keep typing. Because sometimes you may have like 20 signal lines to make the line super long, so they rather have a line break and keep writing in a column instead of the whole line. There could be like 20 signal lines. Just let you guys know. So I0 connect to I1, and then what? Dot what? I1 connect to where? In 2, right? See? I1 connect to in 2. What about this one? So all these sub modules are individual chips you can grab from the drawer in the lab. You grab this one, plug into the breadboard. Grab this one, plug in the breadboard. Let me draw it for you. So grab this guy, plug into the breadboard. Here's the breadboard, is the top module. You grab this one, you grab this one, you grab this one. Yeah, I can connect this one here, connect this one here, connect this one here, connect this one here. Okay? So what about these internal lines? They are not ports. They are not declared. How to do this? So you are thinking, hey, I can do this. If I'm over here, I can connect or out to I1. I1 is going to be input. It's going to connect to itself, like OR gate with the feedback. First design on this planet. Anyway, so it's going to be interesting design, and it won't work. How do we deal with it?
I guess you could specify somehow the exclusive OR input to match with the
Yeah.
OR output.
Yeah, but how?
I guess you do the exclusive OR gate, exclusive OR gate 1 dot I1, and then put OR out.
Okay, so there's a specific way to do that in here. So the way to do that is you create a little wire in your top, because we are now still programming in the top module. Keep in mind. So we are programming the top module, right? Agree with that?
Yeah.
It's at a certain layer. It's at a certain hierarchy here. So here's the top layer. Can we just create a little piece of wire here?
Oh, yeah.
All right? A floating wire, just a wire. You don't have to worry about it. Just call it a wire. And then you connect this one to this wire, also connect this one to the wire. Later, when you are instantiating this guy, right? So this one connect to this wire in that module instantiation. But now we just connect this output to this wire, and just waiting in the future, we connect this one to this wire, the other terminal of the wire, and eventually they will be interconnected. Does that make sense?
Yeah.
Okay, because you are programming the top module right now. The only thing you can do is create a floating wire in the top module. So what you want to do now? Create a wire, right? Okay? Create a wire. How do I minimize it? So let's call this one. I have to make a snapshot, since I can forget this really easily. Let's call it wire 1, W1, W2. That's okay. Do I need a wire here or no?
No.
Why?
Straight from the input.
Yeah, it's a port, right? It's a port. It's available from the top. It's right there. It's already declared. But the wires are not declared. How many bits do you have on the wire? How many bits?
Just one.
Okay. Okay. So what's next?
We do the AND gate.
We haven't finished the OR gate yet, right?
Oh,
So the two inputs for the OR gate, and what's next? The output, right?
yeah.
How?
That'd be dot or underscore out, and then parentheses the wire. Probably wire 1.
Okay. It's gonna be the same, I guess. Let's just type it. I0. Is that in 1 as well? I0 is in 1, yes. I1.
Yeah.
I1 is in 2. And out is.
Make that wire 2.
And out is what?
Wire 2.
Okay. And move to the next will be the XOR gate, right? XOR gate. So be XOR gate 1 dot what? Look at the XOR gate definition here. So I have XOR gates names are also I1, I0s.
Yeah.
Like what I said, it doesn't matter, right? So they can have the same name for the sub modules. They're not visible to the top. So what I can do is, because the names are still I0s, right? I0 for the input, one of the input, and it's connected to what? W1, right? Wire 1. It's on the other side of the wire. And then I do I1 connect to W2, right? No, I1, sorry, I0 to W1.
Yeah.
I0 to W2, I1 to W1, right?
Yeah.
Okay. And output, which is XOR out
Yeah.
over here, right? XOR out to what?
Out.
L1. We can directly use L1 because L1 is the port of the top. It's over here. Right? So and the last one, which is NOT gate, NOT gate 1, it's still using the same name of the port, which is I0. And it's connecting to what?
Out 2.
In2, right?
Yeah, into.
In2. It's in2. And it has output, the name of the output is L2, right? Because the top module is L2.
Yeah.
So the NOT gate out, the NOT out here is connected to L1.
No,
L2, yes. Okay. Colon right. Anything else?
I think it should be.
Do we need the initial begin, assign a delay, and run the simulation? Because usually we do the test bench. Do we need a test bench within that top module right now? Why?
We can add one later.
Yeah, it's not a test bench. Keep in mind, the top here is still a digital design. It's still a chip. It's not a test bench yet. It's still a chip. Okay, you just placed a couple of other individual chips into one bigger chip. It's still a chip. If you need to run a test, you want to start a new test bench and instantiate this top module there and adding all those simulation files. If you're running on the IPGA board, you need the simulation. You need the ports, the test bench, the version for the IPGA board, the hardware. Make sense? Okay. Yeah, that's it. Okay, so let's take a break, and so the quiz will be on 4 different methods: hierarchical, structural, data flow, and behavioral. I'll give you 25 minutes probably. So let's come back at 9 o'clock. We'll start working on the quiz. Okay, closed book, closed notes. Okay, it's gonna be handwriting on the hard paper and turn in person, hard copies. Give you like 8 minutes
Yeah.
to review it and take a break as well. Okay.
So, for only the data flow modeling, you have to include the input?
Yes. I didn't take points off from this.
Oh, yeah, totally.
This is input, output, which works.
Okay,
You can
okay.
keep this.
So could you do that, or could you also define it inside the module and just leave? Because I guess I was kind of thinking, it's like here, it's not explicitly defining what's input or output. We define it. Okay, cool. Sweet.
I'm trying to look at the J-Man example.
The top.
This is top already.
Like the module top.
A module top.
Yes, thank you.